Welcome, welcome everyone. We're looking at question 9 on the 2015 term test 2. We have two parts again, just like in 8. And once again, we have a state, a definition. It really points out, because we had a couple questions like this on test 1, that you really should take a look at those key concepts. The updated file is in our resources tab. It has everything from test 1 and also stuff from test 2. And we'll add to it, I believe, for the final as well. So you can come back and check for an updated key concepts, start of April, that sort of thing, maybe. But take a look at what's written there. Things that are important, like definitions, named theorems, they're there, and they're things that you should know, because 9a is asking us for the monotone convergence theorem. Okay? So that's the first thing I'm going to have to do, and then I suspect the way tests tend to be written that B will have to use A, but let's get our monotone convergence theorem. So if sequence AN is bounded and monotone, monotone or monotonic, whatever you want to say, then the sequence, you could say converges, I'm going to say has a limit. You could say has a real limit, so people who think infinity is a number aren't confused. But that's all we really need. We need bounded, we need monotone. And if you want to, if you have extra time, you could explain them, especially monotone. Bounded, I think, is a bit self-explanatory, but monotone, either the sequence never decreases or the sequence never increases. This is monotone. Okay? Alright, so 9b. Let Sn be the sequence of partial sums for our series here. Just reminding us what partial sums are in case we didn't already know, but of course we know, we studied. Suppose that the ANs are always positive, and that the SNs, no matter what, are less than or equal to 2015 plus the cosine of pi n to the 2015 for all values of n. It's, the n's start at 1. Prove that the series is convergent, and they're even asking me if it's absolutely convergent. Well, it's going to be, if it's, so we're going to have to prove that it's convergent. And automatically we're going to get that it's absolutely convergent because the sequence terms are positive. Okay, I think that's probably the first thing to note. So, it will be absolutely convergent since the absolute value of AN is AN. So as soon as we show that this guy converges, we will have that the absolute values converge because they're the same thing. Okay? And then I suspect we'll probably have to use the monotone convergence theorem. Well, they told me all the terms are positive. So to show monotone convergence, I need to show that the sequence is bounded. So the sequence of the SNs is bounded, and then I need to show it's also monotone. So the first thing I'm going to do is show it's monotone. Notice that since the ANs are greater than 0 for all n greater than or equal to 1, Sn, which is equal to Sn minus 1 plus AN, must be greater than Sn minus 1. So the SNs are increasing. That is, it goes S1, S2, S3, and so on. Now we also know that Sn is less than or equal to 2015 plus cos, I think it was pi n to the 2015. Don't really care what's in the cosine, it doesn't really matter. And here's y. Cosine of x is always less than or equal to 1. So what we've really shown is sine n is less than or equal to 2016 for all n. So my SN sequence is bounded by S1 is the sequence will never get lower than that, and 2016 it'll never get higher than that. Okay, so it's bounded. To use monotone convergence to show that the SNs converge as a sequence, and therefore the infinite series converges, we need to also show... So we've got... Oh, wait, no. I already showed it's increasing. Yeah, they're increasing, and they're bounded... Oh, so I'm done. I thought I had an extra step. Silly me. So, by the monotone convergence theorem, since these guys are increasing and bounded, the limit of the SNs, let's say the limit of the SNs exists. And so by the definition, it's been a while since we've seen it because we have a bunch of other tests, but by definition, the infinite sum converges if and only if the limit of the SNs exists, or you could say the SNs are convergent. So the sum of the ANs converges, and as previously remarked, the sum of the absolute values of the ANs converge as well. And there we go. So that's 9A and 9B. Up next, quite naturally, will be question number 10.